Alright, silly people, here's the situation. We're going to be using matplotlib to plot a bunch of silly looking math curves, which are pretty funny. The first one is the deltoid curve. It kind of looks like a Dorito. Um, and it is given by these equations here. Uh, and its domain is theta is 0 to 2 pi, but we're going to be plotting x versus y instead of r versus theta or anything like that. So let's do that in this cell here. Um, just do, we know we're going to need matplotlib, so let's start by doing that guy. Import matplotlib.pylab as plt. I see that we have cosine functions and sine functions in the problem statement, so we should probably also import numpy. It's the easiest way to do that. And then we make a list of thetas from 0 to 2 pi. So I'm going to do this via a linspace, numpy linspace function. And you start at 0 and you go to 2 times np.pi. And we'll just do 100 points for now. That should be high enough fidelity to see the whole curve. And then we just simply write the equations. So x equals 2 times np dot cosine theta plus np dot cosine 2 times np or just theta. Yeah. And then y was 2 times sine theta, and then minus sine 2 theta. Made the same mistake twice, but yeah, that sort of thing. Just gonna make this a bit shorter. And then after all that, you just use matplotlib to plot x versus y, and you'll get the deltoid curve. Pretty nice, pretty sleek little shape. The next one is to do a polar plot by using the equation r equals theta squared, and then convert those into Cartesian coordinates and plot those. So I'm just going to grab this, or I'm going to grab this chunk of code right here at least to copy down into the next cell here. But then we do r equals theta squared, not theta times theta 2, but theta squared, and then convert r and theta into x and y, so x equals r times cosine theta and r times sine theta, and then just plot x versus y. I think this should be pretty straightforward, and then make sure we have it going from 0 to 10 pi as well. Let's give that a run. It's a little choppy. We can add more sample points to make it smoother. I'm just doing 1,000 for now. But that's not bad. Galilean spiral. The last one is a plot of the phi function. That is r equals that junk there from theta equals 0 to theta equals 24 pi. So I'm going to grab this chunk of code again, copy it into the next code cell, but then make it so that the domain extends to 24 pi, right? And then the phi function itself was r equals e to the cosine theta, so numpy.exponent numpy.cosine theta, and then minus 2 times cosine theta times np.cosine, and it was in the cosine function 4 times theta, and then plus sine of theta over 12 to the 5th, so plus p np of sine theta over 12 raised to the 5. And then convert r and theta into Cartesian coordinates, just like before. R times np of sine theta. And then plot x versus y. And it's going to give us, again, that's pretty choppy. I'm going to add another 9,000 sample points. So you should get a really smooth phase function. That's pretty nice. All right.